So today I'm going to talk about chiral algebras for n equals to 2 and n equals 3 theories. And I'm going to present a collection of results, and not all of the results are my own research. So they involve also some people in the audience, in particular Wolfgang, Magdalena, Carlo, Martina, and Bald, that should be here, but anyway. Okay, so exact truncations in SUSY theories. So seeing that we have an audience of experts and we've had some talks already on the subject, I'm going to start immediately with the conformal block expansion. So I'm in the bootstrap business, which means that I'm interested in studying four-point functions in CFTs. And conformal symmetry implies that these four-point functions have a conformal block expansion. So in general, two-point functions and three-point functions are completely fixed by symmetry, but four-point functions, conformal symmetry is not enough to fix them all, but we know that they have this kinematical constraint that can be written. Where these functions are fixed, they are just some hypergeometric functions. And when usually uses cross ratios U and V, but I'm going to define variables C and Z bar, which are easily related to the standard cross ratios. So C and Z bar are just cross ratios. And the purpose of the bootstrap is to find constraints on the CFT data, basically on the OPE coefficients and on the conformal dimensions of the operators being exchanged. So delta and lambda. So that's the idea, that this one can write a crossing symmetry constraint, and this constraint should impose crossing symmetry equation, and this equation should impose constraints in the system. So that's the idea, but now the question is what to do with this equation. So what to do? And in particular, one can do numerics. Very popular these days, and that has given impressive results, in particular in the 3D Ising model. One can also do the Lightcon bootstrap. We have also some experts in the audience, which this equation somehow simplifies in the limit of large spin. And it turns out that sometimes one can do an exact truncation. Namely, we cannot solve this system in full generality, except in two dimensions, of course. But sometimes there is a portion of it that decouples and that can be studied analytically. But that only happens when we have SUSY. So this is what I'm going to talk about today, about these truncations only with SUSY. So in particular, for the case I'm interested, one can get rid of one coordinate. We get a crossing symmetry equation that depends on only one variable.
So this is only for theories with supersymmetry and only for protected intermediate operators?
Well, that's the thing. The only ones that are going to survive are going to be protected. So, and just the first part of this talk, especially in class 2, is going to be kind of a review. So I'm not going to give you all the details of this construction, but I want to give you an idea. And
sorry, and this is in 4 dimensions? Or?
I'm going to list when it's possible. So, first question is what happened with C, with Z bar. The easiest way to understand it is with an example, and in particular the n equals 1 chiral way. So in n equals 1 theories, one can define chiral operators, but we know they are killed by one of the supercharges. And in particular, the superconformal algebra fixes the momentum operator to be Q exact. You know, it's the anti-commutator between two Q's. So we say that the translation operator is Q exact. And in particular, derivatives of the field phi, this chiral field that is killed by the Q's, it's also Q exact. So the derivative of a field phi can be written as a commutator beyond phi, and this can be written as actually Q on something. Then something I'm going to call X. And all of these are basic statements, but these basic statements imply in particular that the derivatives of correlators with respect to X are 0. So this is a quantum mechanics exercise. You can check that given these 3 properties, when you take the derivative of a correlator, you know your commutators, and you get 0. And so the lesson that we get from this classic example is that if you want to get rid of a coordinate in some correlator, in particular in this case X, find a supercharge such that operators are killed by this Q and that translations are Q exact. So if you find such a supercharge, then you can get rid of the coordinate. That's the idea. And that's what happens here. So here at the beginning, we have a crossing equation, a correlator that has 2 variables and 2 cross ratios, C and Z bar. But we can find a supercharge such that this phenomenon, or small variation of it, can be applied to Z bar.
So it's a specific translation, or is...
In this case, this is the example, just to get you the idea, this is just translation in X. This thing, you kill all the coordinates. This is a bit too extreme. Here is more interesting because you kill one coordinate, but then you have some structure that you can play with.
But sorry, but could you put some index in the delta and then say any coordinate?
Good. Yes. So let's first I.
Yes.
I can be
any mu or whatever.
Yes.
Good. Very quick.
The alpha beta with respect to actually it's d dx I mu. And so the question is, when can you do this? And so the following systems, there is a supercharge such that you can get rid of in 6 dimensions for n equals 2,0 theories, in 4 dimensions for n equals greater or equal than 2, and in 3 dimensions for n equals greater or equal than 3. is very similar to this equation that I got here. You get rid of one of the coordinates. In this one, is a bit more severe, and you get rid of all the coordinate elements. You get a bootstrap equation just for the CFT data.
What happens for 3?
3?
3 and 3. Anybody?
Well, you need, I'm not giving you the details, but you need to find a supercharge that more or less satisfy these conditions. And for that, you need a lot of supersymmetry. And in particular for neighbor 3, it doesn't work. You need at least neighbor 2.
How about in 2 dimensions?
In 2 dimensions, yes. It can also be done, I think you need 2,2, 4,4, 0. Okay. It can be done, 0. Now, there is another system a bit outside this class in which the construction also works, which is B equals 4, N equals 4, so N equals 4 superior means, but with defects. And so you need a lot of SUSY. When you put defects, of course, you start breaking SUSY. But because N equals 4 superior means has so much SUSY to start with, even in the presence of a defect, there's still enough leftover supersymmetry such that this construction works.
And there's presumably similar statements in D equals 3 with higher, with N equals 8 or N equals 6?
I don't think so.
No?
I don't think so. We discussed with Madalena and Carlo, and I think we didn't find examples.
So we get the line, for example.
Right. That would be a 1D example.
Presumably also D equals 6 is the co-dimension to defects in
Yes.
Yes.
True. Also true. Now, and anyway, with Carlo in particular, I'm not going to talk about this example, but we've been studying it with Carlo, and it's a lot of fun because in all these systems, as the equations that you get is a bit too protected. But in this one, there is a coupling dependence. And it turns out that the equations that are captured by these truncated equations are the same operators that are captured that can be calculated using localization. So I'm not going to talk about this thing, but it's a nice interplay between bootstrap approach and localization. Today I'm going to talk about this one. Okay, so that was the review part. Introduction of the review. Now, let's go to this section. So this guy, this correlator, this truncated correlator is a function of C, and the notation is suggested, and it should remind you of a correlator in a 2D CFT. And indeed, that's what happens. So how do we go from a correlator that is a function of 2 variables? Correlator based function of just one variable. So the first thing that you need to do is to put the operator here. So this you have to do by force. The operators on a plane, these ZZ bar coordinates, these ZZ bar cross ratios become literally the coordinates of this plane.
So that you can always do by a conformal transformation.
No, because here you can have 10, if you have 4, sure.
Ah,
and actually,
sure.
I'm going to study mostly the case of 4.
So
But
if you
in
don't have
general,
4, then you don't have set bar cross ratios to start
Sure.
with.
Yeah, correct. Well, you have set the bar for each, yeah.
Goodbye.
Let's stick to correct to 4-point functions.
Right. I see.
So you can always do it indeed, and the city bar become the coordinates.
I see, but what you are going to do, even if you have more points, is to put all of them in
Right.
one plane, and then I agree. It's a illustration.
And so then, of course, we want to mimic that approach, and we should have some funny cue now that kills this operators. Let's start at the origin for the moment. Because these are the ones that are going to have a chance of having truncated correlators. And so the first question is which operators satisfy this condition? The Q is a sum of actually Q and S supercharges with some indices. And the question is which operators satisfy this condition? And you can go through the list of n equals to 2 multiplets. And it turns out that the operators that satisfy this condition, given our supercharts that I'm not writing, are so-called sure operators. And for the index experts in the audience, they are called sure because they are the operators that contribute to the so-called sure limit of the superconformal index.
But that's for, you somehow already jumped to the choice of Q.
Yes, I found a Q, a candidate Q, and now I want to see if its cohomology is not empty.
So how much of what you will say depends on that specific choice of Q?
Well, a lot. I mean, it's of course up to rotations. The Q is somehow tied to the plane that you choose. But yes, that's what started the whole story. There is a Q such that this construction can be made. And I don't want to kill you with indices, but saying that you're asking the Q is roughly Q plus S. With this there. So it's a funny combination. And then
There's no other Q, right? This is the computation.
right.
I mean, there are other Qs that square to 0 that have that annihilate some set of operators, but you can't extend them to the translations.
Right, but we have the second condition that we want some sort of translation operator that is Q and exact.
Right.
And that one we think that this is not, I mean, maybe we fail. So in particular, our construction only works for n equals 2. We could never make it work for n equals 1. Maybe, I don't know, maybe there is some Q there that we make it work for n equals 1.
Would it be possible for you to write down in n equals 4 super Yanimir what are these kind of operators? Is that easy or?
These are a half BPS.
Okay, so they are trace of phi to the p.
Right. And more.
Also, yes.
Right.
Now, in particular, the chiral ones that Mario and Philip like a lot are not included in this list. So in the notation of Dora Osborne, the epsilon multiplets are not included. And now, once we identify our operators at the origin, we start translating them across the plane. And the C dependence is close. the Q translations on the z-axis commute with the Q, with this fancy Q. So I hope I got the terminology right. I think close to what I want to say. And then the z-bar dependence, the ones that we want to kill, it's actually not quite exact. So I told you that I found a case that the z-bar dependence is exact, but it's not quite exact. And so, to make it exact, you have to somehow entangle it with the R-symmetry coordinates. So, long story short, we are in a supersymmetric theory in which we have some SU2R R-symmetry, and therefore we have SU2R indices. And so, the operator that is going to satisfy this condition, it's actually a funny combination. It's like a twisted operator. You have to somehow connect the R-symmetry indices with the z-bar indices. This is because the z-bar dependence, when you start translating, is not quite exact. And so in order to make it exact, you need to contract the R-symmetry indices with these vectors u, which are given one to z-bar. And this is the combination that is, this is the translation that is q exact. So I lied a bit at the beginning. I told you that if you translate in the z-bar axis, you can get rid of that coordinate, but you have to translate in some twisted, funny axis that has z-bar dependence and R-symmetry dependence. But then, now that we found the correct operator, this construction applies, and in particular, correlators of these guys, of these twisted guys, so let's call them OZ, have only metamorphic correlators.
So it's the statement that these operators, of course, depends on CC bar, but if you put them inside a correlator, the derivative with respect to C bar would be C bar.
Right, indeed.
Correlator with themselves, yes.
And here, of course, I only proved that the Z bar disappeared. Now I'm telling you that the correlator is metamorphic, which is a bit more powerful than just an homomorphic function of the coordinate. But that can be proved using the OP. One can study the singularity structure of these guys using the OP, and you can check that indeed they are metamorphic functions.
So UI is function or this is just coordinate?
F is a function. The thing is that
No, the UI is that.
Just
no,
one
so
cell
UI
bar.
is just a vector.
UI is just
You used to do this twist, this funny twist. I is an SU2I index.
So runs from 1
I
to 2.
said it only with words. Sorry. SU2I equals 1, 2, and it's an SU2R index. Because we have an R-symmetry in n equals to 2 theories. So here is the main result that I wanted to get, is that for the n equals to 2 theories, have correlators that seem to be described by a 2D chiral algebra. And so, I didn't succeed, of course, solving the crossing symmetry equation that I showed you at the beginning in full generality, but we got a slice from it. And it has a lot of structures and encodes an infinite amount of selective data.
Sorry, do you understand how exactly I know that, for instance, if you take the correlator of 4 O20s in n equals 4 superior limits,
Yes.
that's highly non-trivial.
Yes.
So here we are talking about some specialization of that.
Sorry, one can do the same for the 20 prime. You can do the
Yes.
same, and you also get some protected correlators.
But okay, I would like to see that.
You know it. It's this F function. When you do the crossing symmetry, there is a short part to.
Well, sorry. I know if you write down the 4-point correlator, the 4-point correlator is on crab, and inside that crab there is F set and F set
Right.
bar.
And the twist, this twist,
Project
once you do it,
Yeah.
all the crab will disappear.
Yeah, so I wanted to understand better that
Well,
projection.
right.
I see. So it's like when you do that, then all the unprotected bit disappears. So that is a projection.
Indeed. And actually, this twist is extremely elegant in harmonic superspace. It amounts to setting alpha equals z, where alpha is the asymmetrical
Very
function.
nice.
So Paul, I think yesterday he wrote
The second rational function
Right.
will vanish.
this is the twist. Once you
Yes.
put that, all the long parts disappear, and you end up with your manifold.
Excellent. Thank you. So you end up with the 3-level result in that case.
Yeah. And but the nice thing is that one can also bootstrap this correlator just by crossing symmetry, and in particular, for us that are in the n equals to 2 business, you can also do it for non-Lagrangian theories. For example, 46, when we don't have a free Lagrangian to calculate these guys, we can just fix them by crossing symmetry, and we did it. So, okay, so we have a dictionary.
Sorry, I keep saying the same thing every day, but I don't think you end up with a 3-level result, right? You end up with a short contribution, which is a bit more complicated. It's like yesterday, it's the same thing as yesterday. So 3-level.
Yeah, you're right. Yes.
It's a bit more.
Yeah.
Well, it's more or less. I don't know how you count it.
So
It's more or less because it's also the 3 minus
But
the
yes,
3
of
from
course,
the
yes.
So actually, you get a specialization of the 3-level result.
Yes,
But they are short of the loss. You don't get from here back. You get later.
you're right. Yeah, you don't get long at 3 level.
Yeah.
Yes. Well, even at 3-level, you get long.
Well, I would like to understand.
But if you take the 3-level, but so the first consideration is that this is independent, it doesn't violate the common parallel.
Yes.
So the 3-level result must capture the parallel. So if you
Yes.
take 3-level result, very simple.
Yes.
Specialized to alpha equals Z,
Yes.
that's F.
Yes. Right.
Okay, a team effort. So, okay, and there's a dictionary, of course. In particular, if you have some 2D CFT, in this case the holomorphic part of a 2D CFT, there should be a stress tensor. And the dictionary is that the R-symmetry current, that it's always present in n equals to 2 theories, once you do this projection, this truncation becomes the 2D stress tensor. And for example, the 4D OPE of 2 currents is completely fixed by symmetry, and once you do this projection to the 4D OPE, you obtain the 2D OPE of the corresponding field. And you can see that it has the same form as the OPE of the stress tensor. So you can go to Olchinski and check if this is the 2D OPE. Or Lagerberger-Schwarz. So, and so, the first entry of our dictionary though is that the central charges don't quite match, and they have a minus 12 factor. And now,
So what you are doing basically, you take the OPE of 2 R-symmetry currents and you project both sides.
right.
And then you
And you
get
end
that.
up with this, and so you identify these guys as systems. In particular, this is going to imply that now we have full Virasoro symmetry in two dimensions. And now, how is it that, why is the stress tensor in 2D related to the R-symmetry current? Somehow we expected the stress tensor of 2D be related to the 4D stress tensor, but it is, because the R-symmetric current sits in the same multiplet of the stress tensor. So linear nu is basically two supercharges acting on the R-symmetric current. So the stress tensor is not quite captured by the 2D chiral algebra, but a cousin of it is captured, the R-symmetry. So this is the one that represents the stress tensor. So, makes sense.
So you could somehow do this when n equals 1 theory?
Sorry?
You could somehow do this when n equals 1 theory.
Well, we couldn't, and also I don't know which. The stress tensor in that case is shorter, so yeah, I don't know which operator in the multiple would represent, but we could do it. Okay, and the other operator that it's almost always there is the moment map. So this is the highest weight of the flavor current. So in any possible theories, you have flavor, and the highest weight of the flavor current is of the moment map. And this one goes to a JZ operator in 2 dimensions. And if you repeat this analysis of the OPE, you will identify you will recognize the OPE of 2 AKA currents. Plus more stuff. And again, there is dictionary. So this K, this is the usual central charge. This K, I'm going to call it the flavor central charge. And the flavor central charge in 2 dimensions is -1 half the flavor central charge in 4 dimensions. And again, where is the flavor current, right? The flavor current is not quite represented in the chiral algebra, but it can be obtained from the moment map. So if you add QQ bar on M, you get the flavor current. So a cousin of the flavor current is represented in the chiral algebra. Okay, and the last piece of the dictionary that I want to write is that because of this Schur operator business, the counting of operators in the 2D theory is related to what is called the Schur limit of the superconformal index in 4D. And so the equality is that the vacuum characters of the 2D theory should equal the Schur index. And sometimes you can calculate these two things independently and check them. At least, usually as some series expansion in the fugacities.
So basically, you will end up doing a 2-dimensional computation, and then when you want to translate these to 4D, you need to multiply by all these numbers. Is that the message?
Well, you can do many things with these kind of algebras. In particular, what I'm going to do is I'm going towards analytic bounds. And in my calculation, indeed, I'm going to do exactly what you said. I'm going to get the things into D, and then I'm going to lift them to 4D and try to get results. So let's do that. Analytic bounds. So let's consider in 4D the 4-point function of currents with its conformal block expansion. Schematically, of course, these things, indices, etc. is very complicated. Now, we certainly don't have the technology to solve this beast, generally. So one can do numerical bootstrap, but we don't even have the blocks for this guy. If you have a Lagrange theory, you can do perturbative calculations, 1, 2, 3, 4, 5 loops, etc. So solving this thing is in full generality is out of the question for the moment. However, in 2 dimensions, we can do a lot better. So we're going to do this kind of lateral projection, which means we're going to look at a slice of this correlate. And in 2D, what you obtain is the 4-point function of stress tensor multiples. But this one is known. This one is in textbooks. Start with a 1 plus C4, 1 minus C4, plus 8. It has only one parameter, which is the 2D central charge, etc. And so we already obtained our first result, because
So if you normalize this 2D stress tensors, you have the 2D central charge occurring in the denominator there, so you must have normalized that.
yes, there might be some normalization. Yeah, in the 4-point function, you usually want to start with the identity.
So you normalized,
There might be a normalization issue, yes.
T over the square root of C3 or something.
Well, you are divided by twice the 2-point function of P with D.
Yeah, right.
Probably, yes. To do this conformal log expansion, we usually normalize the identity to 1. So,
Right.
I'm sorry, maybe it's inconsistent with what we're doing.
So in order to do that, you could take like a free theory, etc., and do weak contractions, right? And then the result,
Right.
will not depend on-
Or bootstrap it, or as I
Whatever.
did, go to cutoff. Go to cutoff. And formulate it. So, so then this is nice, because now we have the 2D perspective and the 4D perspective. And the OBE coefficients are constant. So if I calculate them on a plane, they are valid still in the whole space. So we can solve for an infinite number of OBE coefficients.
So the statement is that you will know the OPE coefficients for all intermediate operators that survive the projection.
Right. And so now, actually, there is a proportionality constant, which is just a kinematical factor that we haven't calculated because we are lazy, but we can calculate. There is technically a proportionality constant here, but we solved for an infinite number of OBE coefficients up to some proportionality constant that we need to figure out. But from what I want, it's unnecessary. So we solve for an infinite number of OBE coefficients. This is just one of them for some operator O. I'm not telling you which one. But the interesting thing is now that once we got the result in 2 dimensions, we can interpret it in 4 dimensions. And in 4 dimensions, the theory has to be unitary, which means it's actually a square, which means that this quantity has to be greater than equal to 0. And so we obtain our first unitarity bound, which tells us that the central charge of 4D theories has to be greater or equal than 11 or 30. And so I just want to recap for you the assumptions that we made. We only assume n equals to 2 superconformal symmetry in order to apply this kind of algebra machinery. We assume the presence of a stress tensor. So some people you can call that locality, the fact that somehow energy is conserved. And I didn't tell you, but to do the calculation, actually to solve for this OPE coefficient, we assume that there are no higher spin currents. And when you do that, you're basically imposing that your theory is interactive. Because there's a theorem by Maldacena and Silverio that if you have higher spin currents, your correlators are the same as your theory. So I didn't show you that, but to solve for this guy, I assume no high spin currents. So this result is valid for interactive theory.
So this is in 4D, the
In
result
4D.
was in 3D.
In 4D. Sorry?
Ma se nasce
Yes,
nuovo,
but it was generalized by Alba in the art, but then we usually call it compensación de cuentas. But then, once we got the bound, we go to the literature to see how we do it with our bound. And so, the famous, I'm going to call it the simplest, although maybe Mario will complain, but the simplest Coulomb branch geometries that we know are the standard one, the famous one, the collider classification. And I'm going to use the F-theory notation in which the ones with AN algebra are called H. So we have some theory that is called H naught with no flavor group, H1 which has SU2 flavor group, H2 which has SU3, D4, E6, E7, E8. So these are the standard rank 1 n equals to 2 superconformal theories that you can obtain in a variety of ways. And their central charges and the flavor central charges have been calculated. So I'm going to come back to this table at some point. In particular, C and K. K, H naught has no flavor, so no K. And the central charge is either an or So our bound is actually optimal. With the minimal assumptions that we made, it is as good as it's ever going to get. So I just want to make some comments regarding this H naught theory. Because I truly believe, and also maybe some of my friends, is that it's probably the simplest example of an impossible theory. Of course, quantum field theory is very simple, but it has some interesting features. So, in particular, it has a 1D Coulomb branch. So, it's going to be simpler than that. With a generator of dimension 6/5. It has no flavor symmetry. So that's a bunch of multiplets that you can forget about. You don't need to worry about it. It's an isolated fixed point, so it has no marginal deformations. Which means that if we ever solve this theory, it's not going to be, the safety data is not going to be some complicated function of a coupling, it's just going to be some real numbers. And it sits at the origin, in a sense, at the origin of any possible theory space, which also implies that we define features. In particular, this multiplet that is present in any possible theory. In this one, it's also not there. I'm not sure what the interpretation of this is, but I see it as another simplified feature. And finally,
I'm sorry. I didn't understand what you meant by the origin.
No, it's just some.
Sì,
It's just this one. It's just this one. This multiplet, this is the one theory that doesn't have this one. So I'm listing simplifying features of this theory, and I want to add more entry to at least that this multiplet is just.
You're talking about the C, A plane or something?
In this case, just the C line, because
The
it's
C
simply
line.
evidence.
Okay.
You're not going to tell us which operators or which.
It's some, for the X, there is some C hat multiplet, C hat or half and half or something like that. And finally, if you put this.
Sorry, may I ask a question?
Yes.
So if instead of that O, you choose the next guy, or
The bound is
things-
weaker.
Sorry?
The bound is weaker.
I am very happy with that, but I didn't ask the question. So, you will obtain other rational numbers, presumably.
Yes.
Do these rational numbers appear in that table?
Good question. I'm not
So,
sure if I did check
do
that.
these other theories also have some absent?
Well, we are going to find them, but in order to find them, we need to add flavor. So for the moment, I haven't added flavor. So in the next
Is the statement that this theory doesn't have a C hat, one half multiplet, or just that open
Doesn't appear.
coefficient vanishes?
Yeah.
So,
it doesn't appear there.
Yeah,
Yeah.
it doesn't appear.
I cannot prove that it's not there.
Wait, but if you tell anybody, we can check it as a state become none.
did the paper?
If a state become none, so that the state kind of disappear from the square,
Yeah.
from the Schrödinger.
Okay, but it doesn't follow from here. It may follow from another analysis, no?
Yeah, I think J1 some had a
I am not sure.
I think that when the index is known for this theory, I think J1 in his index paper claimed that this multiple is actually not there, but I think then we checked that maybe the conclusion was a bit too rushed. No?
Okay, the index counts with signs, so there are always ambiguities in the interpretation, but it's consistent with the.
Okay, but yeah, so seeing that this entry was too controversial. Finally, if you apply the 2D 4D dictionary, the 2D central charge is minus 22 over 5. And this is the central charge of the Young-Lee minimum model, which is one of the most famous minimum models. So that's it. These are my arguments in favor of H0. It has all these characteristics that I consider simplifying features, and on top of that, it has a portion that is literally described by a minimal model, which are like the most classic examples of quantum theories that we have solved.
I'm sorry, the statement no marginal deformations, that's n equal to 2 preserving marginal deformations, or any marginal?
No, so this one in particular is known to be isolated. We can't have any possible series with the question.
And the question is whether there could be n equal to 1 in marginal deformations.
Yeah, I think there are some papers on this also. Yeah, I don't know.
But the statement was n equal to 2.
Right.
So it's kind of curious that you get that constraint by imposing unitarity, and then you end up with the central charge of a non-unitary.
To be that minus sign
No,
already told you that.
Yeah, I understand that. Yeah.
Anyway, so we're bootstrapping it. Because we finally about this theory, and with Martina and with Magdalena, we are applying the analytical bootstrap for this theory, and our results are getting better and better. We're slowly getting into the realm of high precision results from the medical bootstrap.
So what kind of information are you looking for to extract from this?
Well, non-protected quantities, that's what the numerical bootstrap does. So some of the quantities, there are many quantities that are not protected by supersymmetry, of course, and we have no access to them. The only way to access them is really the numerical bootstrap.
So you are bootstrapping this H0 theory?
Yes, yes. So in particular, for example, when you get the chiral ring, when you have phi 5 and you get a phi square, this guy one can obtain numerically. And as I said, we were slowly getting to the realm of high precision for numbers like this, and we have a couple more.
But you're considering the 4-point function of a scalar operator.
Right. And the fact that the conformal dimension is 6/5 is 1.2 is very small, so it's very good for the numerical tools.
Right, so that phi r.
Right. And the blocks are known. Actually, we have calculated them. I'm running out of time, so let's make again the long story short. So we can repeat the story. We can repeat the story for now the flavor. So one can consider now a correlator of currents. And play the same game. Solve this thing using Pietov or Di Francesco and solve for ordinary coefficients. And then impose unitarity, and we get more constraints. And we also look at the mixed system. So 2 J's and 2 stress tensors. So this one gives us access to a new set of OP coefficients, the ones that appear in J and T. And so I'm just going to show you a plot for one of the examples. Landscape. So now we added flavor, so our bounds are stronger now than this 11/30 because we added more structure into our theory. And so what we get looks like this. So we have the C-axis, we have the 1/k axis. Here we have 3/2. Here we have 1/2, and here we have infinity. And these are 2 analytic bounds. So this is disallowed. So any positive theories can only live in this corner of the line.
So you're not doing it zero.
No, now I added flavor, and so I'm not giving you, I can write one of the bounds for easy one. But now I have a more complicated system of correlators, so for example, one of the bounds that you can get where H wedges this dual Coxeter number. So in particular, this bound is this line, and then one can get another bound which is this line. So theories only live in this region.
And that C is C4D?
Yes, now I'm in 4D.
So these are analytic results, no?
Analytic results, completely analytic results, and then we put...
May I ask you, so the line from 1/2 below that was known, and this is yours?
It's this interaction here. It's this interaction. So our 2 bounds interact.
Oh, see, so both of them are yours.
Right. And let's look at the list. So this is the list. So again, the famous rank 1 theories, for me, again, leave somehow the origin of the theory.
So what's the significance of the 3/2 that you've marked on the
that's
1/k?
It's another bound. That's the A. It's another bound, but it's weaker.
But it's weaker.
So and then
we went to the literature and started plotting economic theories. And we have plots for all the flavor groups. So in particular, Professor Wissler found an infinite amount of theories studying compactification to city theories. We calculated we looked at the central charge and they always fall inside our bounds.
So you didn't do an infinite amount of work.
Yes.
So part of that is numerical different or what?
Well, that's the thing. We have a numerical bound, but it's actually very weak. It's like here. But this numerical bound, we found studying only one correlator. The stronger numerical analytic bound, we found it studying mixed correlators. So it's a lesson that we've been learning in the bootstrap business, that when you start considering mixed correlators, your constraints get a lot stronger.
And this bound is independent on the rank of the theory. This does not include that.
The rank is here. So the rank 1 is here and the other.
No. What do you mean? That theory could even be ranked member.
Yeah, of course. We don't know. And so one final comment. We also have similar plots with some very nice intersection for G2 and F4. And these theories are a mystery because they have not been constructed yet. Mario is telling me always that they actually don't exist. So I leave it here as an open question.
Sure. G2 and F4 flavor symmetry or?
Yes, G2 and F4.
I can do option example.
No.
With these values.
A specific value.
With these values. With these values.
With which one?
We reproduce all of these numbers plus 2 more entries here with G2 and F4.
You can do the same thing for each flavor group. There's a different intersection point.
Yeah, I don't know the
values. Oh, and all those theories leave on an intersection point?
Hey, I'm done because the questions are stuck.
So, what do you mean by SU2 landscape? That the flavor group is exactly SU2 or it contains SU2?
It could be a subset also, of course, yeah. But
so this is for any any
at least SU2 flavor.
Any non-empty flavor.
Yes, any non, of course. We cannot distinguish.
It just means that the flavor group contains SU2.
Right.
But there's also U1.
Yes, there's also U1. Have we done something with U1? I don't remember what.
So this fundamental of Z is the SU2 or SU2? So you change the group then?
Yes, of course. I mean,
Well,
this current is in Keter, for example, for any flavor. That's what you get. I mean, their normalization is.
So if you're going to go on and talk about n equals 3,
yes,
you will. From the n equals 2 language, that will be talking about U1 flavor.
Yes, yes. So I'm a bit blocked now, but yeah, that's the thing.
Is the chronological for H1 being identified?
Yes, there are some papers by now I'm getting lost, but probably Cordova or Witten or ours also. This, yes, for all these, for many Argyles Douglas theories they have been identified, and actually they match minimal models.
So, aside from these guys, are there other theories that happen to line up the boundary of what's allowed?
No, and that's very nice because for SU4,
right,
these things no longer intersect. So it's really just this plus G2 and F4.
So you see no inconsistency for F4?
Sorry?
You see no inconsistency in this language for F4?
No.
So this Poppy coefficient that gives you the second bound.
Yes.
Can you remind us which type of multiplet? Is that
it's always sig hat.
But it's not related to exponentiation. That is essentially the question.
It's not related to what?
It's not related
No,
to
sorry. This one, I didn't want to go into that, but yeah, this guy is actually related to a Higgs transformation. It's a big hat And these theories are known to satisfy that particular situation.
Well, that's the bell.
Second part, I'm going to change gears a bit, and we're going to go to n equals 3 squared formal theories. So, in particular, we have Iñaki here, that is one of the founders of the field. So, I'm not going to bastardize his research trying to explain it to you. So, n equals 3 theories, for me, they exist. As a bootstrap person, that's all I know. They were constructed using fancy string theory backgrounds with funny names like S-folds, U-folds, generalized identicals, etc. But from the field theory bootstrap point of view, I just need to know that there are certain conformal fixed points with n equals 3 super conformals. So they have n/2/3 symmetry, and the R symmetry group is given by SU3R plus P1R. This is the R symmetry. The A and C anomalies are the same. So I'm just listing some properties of any positive theories. They have no marginal deformations, so they are always isolated fixed points.
When they're not n equals 4.
Right. Okay. Not n equals 4, of course. The pure n equals 3 ones. And they have no flavor symmetry. Also, in these theories, Higgs and Coulomb branches are related. Basically, the extra supersymmetries relating to each other. And so, for the people that like multiplets, it means that some big hat, some epsilon r in the n equals 2 language belong to the same n equals 2. Okay, and so now we're going to study these theories from the point of view of Pedro algebras. And there are some differences, some interesting differences with respect to the n equals 2 case. So, in particular, when you write the SU2, 2,2/3 group in terms of in n equals 2 language, you get an extra U1 flavor. So there are no flavor symmetries in n equals 3 theories. This is just an artifact. This flavor was really part of the R symmetry in the original n equals 3 theory, but when you break it to n equals 2, it looks like a flavor. But so then, when one studies chiral algebras, there's going to be some flavor current in the 2D theory. So we know that there's going to be a J0. Right? I told you before in the first part of the lecture that when you have flavor symmetries, these flavor symmetries represented by a carbon AK. AKM covered in 2 dimensions. The other operator that we also know is here is the stress tensor, which I'm going to write here. So chiral algebras of inequality theories have a stress tensor. And the interesting thing is that some supersymmetry survives the projection to the 2D plane. Which means that we're going to have now some supercharges acting on the plane. So in the n equals to 2 case, when you do the projection, you use up all of your supersymmetry, but in n equals to 3 theory, there is some leftover that acts on the plane. So then these guys, now the 2 operators that we know have to be there, because we know there's a U1 flavor and we know the theory has to have a stress tensor, actually belong to a 2D multiplet. So there is a generator, an extra generator, so there is some supercharge that lives on the plane. Give me a generator that I'm going to call GZ, another one that I'm going to call G bars. And so for n equals p theories, we collect everything in one big J, which is now a super stress tensor multiplet. So, like in the pure n equals to 2 case, the symmetry is enhanced to Villasoro, and now the symmetry is enhanced to n equals to 2 super Villasoro. So great. So chiral algebras for n equals 3 theory have a type structure, basically, a more constraining structure because they have to have n equals to 2 supersymmetry to dimension. So, in particular, we're going to consider theories of rank 1 again, which means that they are going to have one generator, one Higgs branch, Coulomb branch for n equals 3 theories generator, Higgs branch, Coulomb branch generator. And so I'm going to introduce some notation that you can ignore, but we're going to have a stress tensor which sits in a multiplet that we call in our paper B11. It's a sort of, you can ignore the notation, we're just mimicking Donald's notation. And the other 2 operators that we know the n equals 3 theories that we're interested in have are Higgs branch generators. And this one we call BL,0, and there is a conjugate B0,L for some L. So these are the multiplets. As I said, I'm going to be very practical. I'm going to assume that n equals 3 theory exists. I know that they have a stress tensor, and the simplest that people have constructed, they have rank 1, and therefore there is a generic that is conjugate for the Higgs branch.
These are SU3 weights, in other words? Those in?
Yes. Yes.
So can you say what is the n equal to decomposition of this interval?
Oh, I don't know them by heart, but
it has to be.
Yeah, it's well, this one is this one that I wrote here, basically. And this one, yeah, it's going to have a b hat 1, so I can write it here easily for you. This one is going to be a b hat 1.
Is that J the flavor, J? That's the flavor, right?
Which? This one?
Yeah.
Yes. The big one is now the stress test, the super stress.
So is B1 hat in that operator? Or?
No. Yes. This is a big hat, B1 hat. This one is, of course, going to be the C hat, 0, 0. And these ones are these, for the ones that know these things. So that's a decomposition of this.
So the B1 hat is in the, which one? In the B hat 1, 1 or the B?
In this one.
In this one.
It's a flavor card.
Then you wrote something there also.
Yeah, because it's another type of B.
Oh, okay. So it's not. So this is okay. This is the
Yeah. So one is the Higgs branch B.
Okay. So that's it. operator with the R symmetry also.
Yes, maybe without
Without
a hat, sorry.
Whatever.
Without a hat. Okay, but then these are the operators that we have for B, and once we project to 2D, we're going to get a big J, which is going to be the stress tensor multiplet in 2 dimensions. And these ones I'm going to call double B. And they are equal to two chiral and anti-chiral operators. So in particular, there is a design B bar on W equals 0 and B on W equals 0, where these are some superspace derivatives that I'm going to write in 2 dimensions. And the conformal dimension of this guy is 1, and it has, remember, there is a flavor symmetry which is 0. This one has conformal dimension L over 2, F equals L. This one has dimension L equals 2 also, and the conjugate. Now, what this L means is because the Coulomb-Bruns geometry of these theories has the form Z3 divided by CL. And if I understand the literature correctly, and maybe either Mario or Iñaki can help me if I make a mistake, so these theories have been constructed, have been studied for integer L's. When L, this parameter n equals 1 or 2, the theory has enhanced n equals 4.
Phi, the chiral algebras we just annotated, right?
Right. But phi, I think the geometry is not allowed.
Right.
So this one is out. 3 and 4 have been constructed, the geometry is understood, and they have also been constructed using these string theory constructions, so both of these are good. And this one, the geometry is known, but no theory has been constructed, I think, using string theory. I think this is the statement. Maybe I'm wrong. I don't know. I thought this phonetical sequence was concerned, but maybe it's also good. Anyway, I'm gonna concentrate on this one.
Is it the early fragmented cover?
Yes.
He's right. I think he's right.
Yeah.
I mean, those are specific. Those are not the one that all come from the 3 kg. Right. Usually.
Okay, and the 4 decentral charges of these theories are given by 12 minus 1 divided by 4. So again, from the practical bootstrap point of view, we're going to concentrate on theories, first of rank 1, that have a Higgs-Brown generator with a big hat 3 0, which means that in the 2D theory we're going to have a guy with dimension 3 over 2. And so how do we construct the chiral algebras associated to these theories? I think this I call section 2 in my notes. So there's no deep section 3.
Sorry, I'm being a little bit stupid. If I have a chiral operator of dimension, 2D chiral operator dimension 3 times, doesn't that look like an additional supercurrent in the 2D chiral algebra? I feel stupid.
But there is also a conjugate, so.
Okay, maybe
if you add, if you have a 2D CFT, there's a whole big current or something. But this one is close, particularly this one is in the upper.
Oh, this is boson.
Yeah, it's bosonic, sorry. It's a bit.
I see, okay.
Yeah.
Okay.
It's a bosonic field. It might be a bit funny.
That is funny, yeah. Okay.
But these are, we're in the world of non-unitary theories, so it's fine. So this was work done by Nishinaka and Tachikawa. So they constructed a chiral algebra that describes these rank 1 theories with one Higgs-Brown generator of dimension 3. So in order to do that, they use a two-dimensional superspace. So big Z with coordinates Z, theta, theta bar. And we have two covariant derivatives. Well, superspace derivatives. Yes, that should be a theta bar. It's not on my notes. No, sorry. No bad. And so the idea now is that somehow to bootstrap the chiral algebra, right? To construct the chiral algebra using consistency requirements. So we know that our chiral algebra has three generators. The tensor, the two chiral fields. And now I have to start writing OPEs in order to construct the chiral algebra. So the OP of J with itself is completely fixed by superconformal symmetry. And you can go to your favorite 2D book and look it up. We start with the 2D sense of charge plus some fermionic coordinates J plus dot 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 plus. So this guy is completely fixed. Then these W's should transform as conformal primaries, which means that the OP is also completely fixed. So because they are primaries and they have dimension 3/2 for the case that I'm interested, the OPE has to start with 3/2 and the thetas. It has to start 3/2W plus dot 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 dot. So far so good. Finally, the last entry that we need is the OP between W and W bar. W and W is actually regular. You can convince yourself that you cannot write anything on the right hand side, and W bar all the right force. So in a sense, the only non-trivial OP coefficient is WC1, W bar Z. So this one I'm going to write with a bit more detail. So there's going to be a sum from H0 to 2, so from operators that have 0 conformal dimension, operators that have 2 conformal dimension. The power of Z is fixed. And 3 minus H/2, theta 1, 2, theta bar 1, 2 over Z 1, 2, plus 1 plus theta 1, 2D. Okay, so that's the assets. It's a sum over all possible operators that have the correct quantum numbers to appear on this side of the equation. So these OH, these are coefficients, arbitrary for the moment, and these OH are operators of dimension H. So for example, O2 you can tell me which operators of dimension 2, which are also have no flavor symmetry, no flavor quantum numbers, can I write? And you can actually write J squared has dimension 2, BD bar J has dimension 2, and J prime has dimension 2. And then O1 and O0, that's homework. You confuse them.
Sorry, what is J prime?
The derivative with respect to just the z coordinate. So DD bar are the fermionic derivatives, and prime is the derivative. And so this is the ansatz, and the question is
why the ansatz has this theta 1, 2, d all alone?
well, it has to be consistent with the fact that these two guys are conserved. And if you work out your derivatives, you will see that this is the most general form consistent with the conservation condition of these two fields.
So this ansatz is asking that this algebra closes.
Well, now we're going to answer, right? So that's the thing. We know that these theories exist. We know that they have these fields. So Nishinaga and Tachikawa said what is the chiral algebra, and they did a minimal assumption. We're going to assume that the chiral algebra has only these three generators. The OPEs have to look like this. This one is fixed, this one is fixed, this one is not fixed, and the question is, are there alphas now such that this whole thing is consistent?
It's not just that it has three generators, but those generators close among them.
Right. So, and that's what I'm going to do now. So in order for this thing to be consistent, you need to impose Jacobi identities. And the Jacobi identities will fix these coefficients, and maybe there will be a solution, maybe there will be no solution. It turns out that there is one solution. They found one solution, but the Jacobi identities are satisfied, so the algebra closes only when the central charge is minus 15, which in 4D corresponds to 5 over 2. And provided that there is one null condition. So you will only get closure of the Jacobi identities if W times W bar is roughly J cubed. But so if you look at the central charge that I gave you before, it's precisely the right value. So they got it right. They got it. They assume that these are the three generators. They check closure of the algebra, and indeed the algebra closes only for this value of the central charge, which is the same value predicted by other means.
What do you mean by
right?
Sorry?
This is L equals 3.
L equals 3. L equals 3.
What is that J cubed mean here? I'm confused.
Yes, it's the current. Sorry, I changed. I call it curly, but I'm going to call it curly.
No, that's fine.
It's a null relation.
But
it's a null relation in the chiral algebra. This is a null that you can build a state that has no norm. And I can write. And indeed, it's expected because these theories, the people that study the Higgs branch, they knew that this type of Higgs bond relation was expected. So they really rediscover everything. So that rank 1 chiral algebra is for sure correct. Describes theory.
In physical terms, what does the relationship mean? You said that because it's expected from the Higgs branch.
Well, some relation of the operators from the Higgs branch. From me, for a bootstrap person like me.
It's just that they are in.
So both W and W bar are chiral?
Chiral and anti-chiral.
And what's the relation of the, so this is superfields?
Yes, these are superfields.
Is it index?
No. Well, they have a theta expansion.
So can I say that naively this is meson bar equal to stress energy tension to the therm? This is this equation.
Okay.
Very naively.
Okay, so now this part of the talk is going to be a lot. The second part of the talk is going to be a lot shorter. I just want to tell you some work that we did with Madalena, with Carlo, and with Vladimir Mitter, in which we try to generalize this kind of algebra construction. And in particular, more theories were constructed. So using this S-word construction, n-3 theories of higher rank were also constructed. And so these theories, now instead of having a generator of dimension 3, they also have generators of dimension 3, 6, and so on. And the central charges were also calculated. And they can be written in terms of the rank. And so in the 2D chiral algebra,
this is the 4Ds.
Yes, the 4D central charge. So in the 2D chiral algebra now, we know that we're going to have the stress tensor.
You're still at L equal to 3.
The two car, sorry?
You're still at L equal to 3.
L equals 3.
Yes, L equals 3 is rank 1. So for L equals 1, you recover the 5.
No, L.
L equals 3, yes. That you can see from here. So indeed, this is always L equals 3. So this is the higher rank version of these L equals 3 theories. And you expect all these generators in the chiral algebra and maybe more. So to generalize the result of Nishinaka and Tachikawa for chiral algebras of higher rank, we need a lot of work, of course. So we decided to concentrate on a subsector. So we argue that there should be a subsector of these chiral algebras that can be studied somehow separate. So in particular, these guys have very high flavor of the central charge. So for example, if you consider only these 3 guys, so I know that there are more generators in the chiral algebra, but if I only consider these 3 guys, somehow these guys should not appear because their R charge is just too big.
What?
Their flavor charge is just too big. But then we have kind of an inconsistency. But we know that these guys have flavor charge that is too big. So we can restrict to these 3 guys. But we also know that there's only one solution when the central charge is close to pi over 4. So what are the chiral algebras that describe these higher rank theories? So that's what the question that we asked with Carlo, with Madalena, and with Jean-Pierre. And so if you look at the answers that I already erased, the J is completely fixed, so there's no freedom there. The transformation of W is also fixed because it's a primary, so there's no freedom there. So the only freedom that we have is somehow here. And indeed, you can check that the only modification that you can do to this chiral algebra is to add some extra generator, a new guy that will appear for the first time in this ODE. So we added an extra operator that we call U that has dimension h equals 2 and flavor 0. And so our assumption is it just has to be. It has to be. There's no other way. There's no room in order to unfreeze the central charge. And so basically we repeated the same game. And now we have some extra, the new operator U is a primary, so it starts with 2ZU plus dot dot dot. W acting on U, we need some alpha 1 here, some coefficients that will be fixed by the Jacobi identities. Plus dot dot dots and more alphas, of course. And finally, the beast. We also need to give an ansatz for U with U, which has very high dimensions, so this thing has an insane amount of terms. So, an assumption, we're going to assume that all the operators that appear on this right-hand side can be written in terms of J, W, W bar, and U. So, we're going to assume that no new operators appear. The U, we needed it in order to resolve the inconsistency, but now here we're making an assumption. We're going to assume that no new operator appears. And the question is, do we have closure of the algebra?
And again, when you're writing the W's here, you just mean the W3s, because you're...
Yes, that's the thing. Because these guys have too big flavor charge, we want to find a subsector. That's what we're going. We want to find a subset of these W's are just the W3s in this case.
What do you mean by too big of a charge?
They have 6. So if you can see that with the OBEs of these guys, we never generate one of these. Just because of flavor conservation.
The flavor charge of W is 3 and W bar.
3, this one is 6 and this one is 0.
So in all their OPEs, they'll never reach flavor 6. Well, but that one's regular. So you only get W, W.
Oh, W bar.
Okay, and so we repeat the game. We impose Jacobi identities. And in our ansatz, especially in this piece, we had 125 arbitrary coefficients. After imposing the Jacobi identities, we can fix 120, which give us one free parameter, which we can identify with the central charge.
This is for rank 2?
Well, that's the thing, we don't know. We want to find the chiral algebra that describes the higher rank. And the rank, the central charge increases with the rank. We knew that this chiral algebra that Nishinaga and Tachikawa constructed has fixed value, so that chiral algebra can certainly not describe this theory, but we said we need to find some modification. And the simplest modification that we thought of was to just add one extra generator. And it turns out that this algebra closes. It doesn't include them all, of course, because these guys are not there. So our claim...
What's the first charge do you get?
Free parameter. Whatever you want.
So their guess is if you included the higher W's up to some number, you would fix that.
Exactly.
How much effort does it take to solve those equations?
Sorry? How long? Well, there is a package. There is a mathematical package, and
so these are not linear equations?
Yes, no, they
Are linear?
yeah, somehow linear.
Some of them are linear, and you get there.
Usually.
So these are coupled quadratic equations in 124 variables. So the solution is numerical at best?
No. It's analytical.
So there must be some, it's not generic.
Yeah, sorry. It's these alphas, you start finding relations among them and you start solving them one by one. And at the end of the day, it turns out that in order for the derivatives to be 0, the alphas can be written in terms of one parameter. And
it's just a very special quadratic system to be
right. And so we have
then
So, do you see in all these any signs of the fact that n has to be integer?
no, in our construction.
Just a very technical. If you would use Virasoro symmetry, you would have like 3 or 4 or 5 confusion.
No, but we super
Virasoro, yes.
of course. Okay.
If you would, and these are linear equations that impose super Virasoro, and then you will find quadratic equation for order 3, 4, 5 confusions. We didn't do this.
So our conjecture then is that our beautiful algebra describes a universal subsector of this element.
But does this, since it's quadratic, does this mean that you have only one solution?
Do you pick some signs from?
Or there is
Yeah, I mean, when we were solving this thing, imagine we have 125 coefficients, we were solving, then plugging back, solving, plugging back.
But do you have a choice of which two things?
Yeah, most likely we have. Most likely. But yes, I mean, it was very painful just to find. It was very painful to find the one solution that we had. So the claim, the conjecture is that it describes a universal subsector. For the L equals 3 higher rank. N equals 3 cubes. Let's call it rank.
Then answer, if you change the sign of some of these operators, the alphas will change sign, right?
No, sorry, but which signs?
Let's say I change u to minus u, and I look at the second equation, wouldn't that change alpha 1 to minus alpha 1?
But that's a bit weird, right? I mean, this number should be 2. No,
No, that's not.
Even in the
Yeah.
In the second equation,
Right.
I change u to minus u.
So some of the signs are not important.
So you should see that ability too, but it's just figure that.
Right. There is, of course, also some overall constant there. Anyway, now, are we... this is our conjecture. Is it true or not? I mean, we don't really know, because here, more things could have appeared. We assume that on this side of the OP we only get J double over U, but for example a new operator O with dimension 3 could have appeared. And then you have to include that one and impose more OP coefficient. So we opted for the minimal solution and we crossed our fingers and we found a solution. So this is our conjecture, but the only support that we have is elements. Because we just added one generator and we unfroze the central charge, which is so true or not, we'll see. But ideally, if we're correct, this kind of algebra describes the protected subsector of the higher rank algebras. And the same thing now could be repeated for n equals 4 and n equals 6, etc. We haven't done it because it was a bit painful.
Tachikawa finds multiple solutions, right? So another now, yeah, because some else needs to have like 3 or 4 solutions.
I don't remember actually.
I'm sure that there is. Huh? Not for everybody, right?
Yeah,
not for everybody. Yeah.
For other
4 and 6 or something like that, kind of two.
So does that change the story?
Well, they haven't done it for
I think 2 hours of talk is too much, so I'm going to finish it.
Could you say, how do you know that the WW OPEs were regular? I didn't understand that.
I think you cannot write anything that has the right quantum numbers. Given this, I mean, WW has a huge flavor charge, and on top of that, you need to these are conserved. So whatever you put on the right-hand side side has to be given by t bar. So you can convince yourself rather fast that you can really, there's nothing you can calculate on the right hand side.
And when you have multiple generators, did the W, do they
I
form like a
checked it
chiral
last
ring?
night, and I think it's still true. I got a bit worried last night when I was thinking about that, but I think you can write it.
It comes in as a leading, like a chiral ring. That's W cubed is just W6 with no. Is that chiral ring something you expect from, or tell you something about the rank 2?
I don't know by ignorance. I haven't studied it. I'm not sure whether people know, for example, Higgs branch relations with these theories. Which, for example, I should say that we didn't need to impose. When we got closure of the algebra, we did not need to impose null states. So that's something that I don't know. We should, open question.
I think kind of just the way Higgs branch geometries in n=4 theory are very constrained. They're sort of flat orbifolds of products of R6. I think there's something that's probably similarly true in the n=3 case. So there may be a check like that.
But what are the properties you would say about the Higgs?
No, for the higher rank, we cannot say anything. Once, as a beginner, I haven't studied whether people have studied the Higgs branch. From our analysis, we don't get any sort of relation. For the Tachinaka-Tachikawa example, they get a relation that can be interpreted as a Higgs relation.
But even before we talk about relations, what is the dimension of the Higgs branch?
Well, I mean, Higgs branch and Coulomb branch are kind of the same in any perspective. We're studying, in this case, theories of rank area. So,
also, you say, first of all, there is no separation, there is a
yes.
single normalized space.
Yes.
So it shouldn't be called Higgs branch.
Well,
just call
Higgs,
it
Coulomb,
yeah. Enhanced Coulomb.
I don't know.
just moduli space.
Yes.
It's not Coulomb branch, just moduli space. It's a single component. This you know.
Well, we have the experts here.
No, I don't know how we know a priori that it's a single component. Why couldn't it have some finite degenerate?
What's the dimension?
No, the dimension
turns out
is n. They have n.
The complex dimension is 3 times n.
3 times n?
Yes.
So it's not even Heisenberg.
No, it's a Coulomb branch. I mean, it's just, it looks a lot like an n=4 moduli.
So it's an orbifold by some value function?
Probably. And maybe they're more general groups than you just thought. They're just complex reflection groups.
But most likely orbifold. So,
yeah, well, we could probably, I'd like to discuss it with you. I mean, maybe.
Okay. Maybe we can figure out something. I see.
Any other questions?
So here, rank 1 theory, I thought to mention GC modeling, maybe some of brains are at the origin, but those things does not affect the field.
Say the question.
No, so from equal 4 to get an equal 3, you do some sort of GC modeling, and then if you study, say, 3 GC brains, then you identify with GC. But if I have 4, I have to put 1 origin, then do you have additional operators?
No, but the claim is that all brains contribute in the same way. So if you fix one to the other, you lose the dimension.
In some cases, you can think of a stack brains.
Yeah, at all, right.
So, in the C2 case, for example, that would be interpreted as a discrete agent.
Discrete what?
Discrete agent. In the other cases, you can still do this discrete agent, but there's no brain interpretation.
There are no other questions? Let's